Most recently, Patty has published in the field of atmospheric chemistry changes caused by anthropogenic climate change. Her goal is to stimulate discussion and action. Global civilization is under an existential threat now at the close of the Holocene epoch, which is to say this 10,000-year-long phenomenon with the regular seasons and stable climate, which gave rise to agriculture. At today's juncture, thanks to the impactful industrial age, we're accelerating from the Holocene to a new age characterized as the Anthropocene. On this subject, Patty provides an honest, sane, integrated, planetary level perspective.
Woohoo!
Thank you. Thank you very much. Aerospace Corporation, which is a nonprofit under contract specifically to the USAF, the United States Air Force Space and Missile Systems Center in Los Angeles. So we participated in making sure the weather satellites and the geostationary satellites and all got up. We were launch integration. And I worked in the Ivan A. Getting Laboratories, which was a stable of about 300 top-level scientists and technicians and so forth. And if you're going to have a bunch of scientists around, you've got to do care and feeding of them. And the way you do that is to give them a research budget and let them work together and do research in their own little ivory tower, which is what I did. But I got into a lot of the applied end of it because I'm an interdisciplinary scholar. So before I start talking much about my subject today, the first thing I wanted to mention, I wanted to clarify a couple of words, and there's a lot of discussion in the media these days about the importance of what I think or what I believe versus what I call facts. And I'm going to show you what I mean by a fact, and it should be pretty clear. And there's a lot of people who believe these kind of things, like we're heading for a Jetsons future, or there's this guy Elon Musk who is spreading the myth that we're all going to move to Mars pretty soon. These are beliefs. And I can discuss any of those if you're interested. But what I want to focus on is what I'm calling facts, which is the science that underpins things that we all rely upon now, without even knowing about it. Radio, electricity, television, refrigerators, pacemakers, antibiotics, MRI, and many other things. Weather satellites, internal combustion engines. You probably all came here in a car powered by an internal combustion engine. You just take for granted. It's because the science has all been done on that. And the way the science is done is with these things that I call facts. Now, they're not all equations, but it's easiest to talk about equations. There are verbal facts, like the laws of thermodynamics, that are expressed not in mathematical equations, but by words. But so things like Newton's law of gravitation, the Navier-Cauchy equations are used for strength of materials, so you can't build a Harley-Davidson without knowing these equations. Maxwell's, sorry?
He said, huh?
Oh, Maxwell's equations, which govern electromagnetism. And the Arrhenius equation, which governs chemical reactions, how fast or slow they go in your body, enzyme reactions and so forth. And then the Navier-Stokes equations down here. These are just some examples of facts. I'll illustrate the first one. By the way, if you combine the Arrhenius equation with the Navier-Stokes equations, and these equations are for the flow of fluids, like around a sports car or something, then you can get combustion, like in a rocket engine or in an internal combustion engine. And it's really remarkable what people do with these things. I'm going to zoom in on a couple of those, but first I wanted to mention a lot of things that I hear people don't know about. In 2003, Florida Appellate Court ruled in the case Acri versus New World Communications that the U.S. news does no wrong when it distorts the truth. So the U.S. news doesn't have to tell the truth. That's just a legal precedent that was set. On the other hand, Canada has a Radio Protection Act, which says the news must tell the truth. So the U.S. news can't broadcast in Canada, for instance. And that's mildly dangerous because of this. So when you talk about scientific facts, like gravity, like here's an illustration of gravity, right? I can predict the future with absolute certainty, so I would call that a fact. When I let go of this, it's going to go down. And everybody knows that's like trivial, but it's knowledge, and it is going to go down if I let it go. So that's just a fact. And that's one of those scientific equations. Which is there, Newton's law of gravitation, which says the force between two objects is equal to a number called the gravitational constant times the two masses divided by the distance squared between the center of those two masses. So it's a mathematical equation that describes a fact that I just showed you. And if anybody doubts that fact, like maybe you think you can levitate, you just say to them, okay, well, step up onto the roof and step off. He had to test it. Yes, it does fall.
Skeptic.
True dat. But I'm going to talk about Maxwell's equations and give a demonstration in a minute. But first I wanted to mention this. Okay, so when you have a mathematical fact, you can predict the future, there are well-defined mathematical things you can do. For instance, if these are the temperature readings along a length of metal, you can get the average temperature. You know how to do that. You just add them all up and divide by the number of readings, and that gives you the average temperature. And that's because nature invented metric spaces, point set topology back in the Big Bang. Also thermodynamics, quantum mechanics. So now we understand the facts of the universe, why that our common sense works on that. But there are no such underlying facts or science of watching, say, like a liberal channel and a conservative channel, the news, and then kind of trying to find the midpoint between them. There's no physics there at all, no mathematical equations. So it's kind of dangerous to use your common sense and think, now I understand because I listened to a Republican and a Democrat or something like that. There's no physics there at all, so you're really just guessing. And that's a belief, not a fact. So I'm not going to talk about those kind of things. But I did want to mention that that's kind of a concern. The other thing is the power of hidden facts. For instance, if I tell you I have three numbers, you can get the average. You add the three together and divide by 3. And you get the average, which is, in this case, 3. And then I say to you something like, oh, I have 4 numbers, but there's 3 of them. And you kind of go, well, it must be small. So you think, well, maybe it's 3, but you might be wrong, very wrong. And this is the power of a hidden fact. So that's what makes that ACRI versus New World Communication so difficult. They may leave out a very fundamental fact that changes their whole story. And they haven't really done anything to you, and you have no idea if they've left out that fact or not, because they're not going to tell you. So mentioning the Florida appellate court. I don't know why I did that. There we go. So I mentioned Newton's law of gravitation. Now I want to talk about an electromagnetic one. This is Maxwell's equations. These 4 equations determine how light works, how X-rays work, radio waves, even electronic flows in computers. And I'm going to zoom in on one of them, which is this one. It's called Faradays Law. And if you haven't had calculus, this kind of looks like Greek writing, but those first 2 symbols there, the delta and the X, just mean the curl or circulation. Like if you stir your coffee, it makes a little vortex. It's saying how big is that vortex? Not big in size, but how fast is it spinning? That's all those 2 things mean. And then the E means the electric field, which is like static electricity. It has an attraction. It'll suck a piece of lint onto your... So this attractive field curls if, that's what the equal sign means, the magnetic field is changing. That d by dt just means the rate of change of the magnetic field. Now there's more subtleties in here, but it's really a fairly simple thing if you know the secret of knowing those things. So I'm going to demonstrate that, hopefully in a way that you can see. So this is a magnet, a fairly big one, and the magnetic field's going right through there. And it's a fairly strong magnetic field. And then I built the other day a curlometer, which the electric wires go around like that, round and around. So if the electric field is swirling like a vortex, you can imagine it's going to carry the electrons in the metal wire, and that's going to cause a current. And current is what lights a grain of rice or grain of wheat light bulb. So I should be able, by changing there's no magnetic field in there now, or a very small one. By putting it into there will suddenly be a big magnetic field. That's a rapid change. So a big number here means there should be a big curl in the electric field, which will cause electrons and light up the wire, light up the grain of rice bulb. So I gotta have my third hand here, and then I'll give it a shot. You might want to stand up. You know what? I'm gonna close.
I'll get it.
Well, no, you won't be able to see the flash of the bulb. Thank you very much. So I have to get the magnetic field rapidly in there, so I got to put it in and out really fast. So if you need to stand up to see this.
Yep.
Yeah, so it's the currents flowing back and forth through that wire as I go in and out. But that's the exact same demonstration as this one. It's just the action of a simply known fact. And all of those equations that I showed, Navier-Stokes equations, the Arrhenius equations, can be similarly demonstrated, but this one's pretty graphic, you know? I like that. It's pretty easy to do. And it's like, whoa. But of course, you knew that was going to happen, right? Because that's how generators work. At the dam or wherever they're making, they spin something in a magnetic field, loops of wire, and that pulls the electrons along in the wire, creating voltage. So, okay, that's that. So those are demonstrations. That's what I'm calling facts. They're just things that are not disputable. Like, for instance, is there life in the universe other than on Earth? That's disputable. People go back and forth about that. So just to recap, the Navier-Stokes equations, and they're really just force equals mass times acceleration, which you might have heard as Newton's laws. But you can, if you add the Arrhenius equation, then you can do combustion, because the equations model the flow of fluid through that torch, and the fluids are oxygen and acetylene. And then they mix and ignite, and it captures the chemistry of ignition and combustion. I'm going to show you a little bit of that. So I got some videos to show. These are kind of fun. This is done on software you can download and run on your computer. So anybody who's sufficiently motivated, like the young man over there, you could download OpenFOAM and design an airplane, make sure it works right, and it would fly the first time. You don't have to buy aluminum and get a license to build and fly an airplane. You can do it in a computer, then you know it's going to work. That's how good our understanding of these sorts of physics are. And it's so, when I was young, this didn't exist. Because, you would have, the software didn't exist. You'd have to write your own software and run it on some sort of supercomputer. Now our cell phones have so much power, as you know. So here's another application of the Navier-Stokes equation. Just yell out really loud if I start talking too fast or I say something and you want me to clarify it. Feel free to interrupt. So here's another application. It's for the flow of the atmosphere over the surface of the Earth. And the way these models are solved, if you see on the back wall there's a grid. That grid actually goes all the way through, but it's been taken away for clarity. They show one grid column, and that's zoomed up to here, and you can see all the grids in there. And then each one of those little boxes is zoomed up to here. And each one of those boxes, the computer solves the Navier-Stokes equation for that box. Now there are millions of boxes in here, so it has to go through and solve every one, and that's one time step. Like, typically these things will run a few seconds of real Earth time. And then it'll go through and calculate them all again, and that'll be the next 3 seconds. And it just does this over and over again until you get a weather prediction tomorrow or next week. And these things are running on supercomputers all the time. They run them constantly. And then every 6 hours, the new satellite data comes in, and they meld it into the existing computer run, and it corrects it, and they just keep doing this on and on. So there's this constant calculation for the whole planet by the National Weather Service that uses all the satellite data. It's a huge enterprise. Now here's an example of combustion. This is dodecane being squirted into about 650 degree F or C background. There's pre-ignition, there's ignition, because it's temperature, right? This pre-ignition is really important. Now this is the HO2, not H2O, but HO2. That's the peroxy radical. It's the key chemistry. That was one of my research areas in causing pre-ignition. And you can't have ignition without pre-ignition. And that a lot of times, if you have that, then you have knock in your car engine. So ignition is a controlled thing. But this is done on a computer. It doesn't look like a computer, does it? But some supercomputer somewhere, this is some graduate students' work in chemistry modeling. So this is difficult chemistry. The atmospheric chemistry is much easier. Here's another one. You can run this in your home if you have a big enough computer. This is Katrina hitting New Orleans. What you can see here is the atmosphere is very thin. That's all the thicker our Earth's atmosphere is. That's why we can affect it by releasing carbon dioxide. It's not all that big. I mean, I know it looks big, but it's only a few miles going up of the effective atmosphere. Did it again. And then this is also run on a computer. So what this is two liquids bumping into each other. This is an injector in a rocket engine. It's called an asymmetrical doublet. You'd have liquid oxygen and you'd have kerosene or fuel that would hit each other, and then they'd spray out into these very fine droplets, which are necessary so they can evaporate and burn. You can't burn the liquid, you have to evaporate it and burn it. So this is the kind of power that our computers have, and the codes are free. For instance, the NASA Goddard Institute of Space Studies Model E, which is one of the US contributions to the IPCC climate model stuff, you can download that and build it on your computer and run it. The problem is, it takes about 44 processors, so you have to have a pretty big workstation. But you can buy those now. It turns out the whole last generation of servers is on eBay now for like $200. These were $20,000 computers 8 years ago. And yeah, so you could build yourself for about $1,000, that's less than a good laptop, a computer that'll run a climate model in your living room. Till they're gone. Once they're all gone, they call them, the term is server pulls, because they just want to get rid of these servers and get the new generation, so they sell them by the pallet, and then somebody on eBay does that. Here's WRF. It stands for Weather Research and Forecasting Model. This is the user page. There's a forum where people will help you set it up. It's the exact same code that the National Weather Service uses. And this is OpenFOAM. This is world-class solver that's like Linux. It's open source software. You can just install it on your machine. You can install this on anything. And the complexity of the model dictates how many processors you need. But for instance, here's a model of a guy riding a motorcycle. And you can see the grids. And in each one of those cells, the computer model solves the Navier-Stokes equations. And that's how you get the flow around that airplane and so forth. So that was about computer models, which are cool. Oh, I know why that's doing that. Because I'm touching a mouse pad. So now I'm going to cut into satellites and orbits, space debris. So this is, in your mind, I like having a perspective of things. So you can tell from this curvature here about how big the Earth is. It like goes way down below the floor in your mind. Imagine that's the size of the Earth. Here's the little bitty skin of the atmosphere that we live in. The ozone layer that intercepts the solar ultraviolet to keep us from, life couldn't exist without that. There's also magnetic field lines, and what happens is the nature of those Maxwell equations I show you, the charged particles coil around the field lines. And so it's shown doing there. There's all sorts of stuff going on. That would be a graduate major, would be atmospheric science. This is a little closer up. It shows you Mount Everest and gives you an idea. The ozone layer is about that far, about twice up as Mount Everest. Shows you where the WB-57 flies. That's NASA high-flying aircraft. The SR-71. The shuttle's flying about here. ISS is here. Hubble is here. The top space begins right about here at 100 kilometers. That's called the von Karman line. And rockets typically take off from either Vandenberg, which is the west coast launch range, or Cape Canaveral, which is the east coast launch range, and go up through most of the atmosphere and then turn over and start accelerating around the Earth. You have to get up to about 7 or 8 kilometers per second in order to stay in orbit. So that just gives you a perspective of what we're talking about here. Some satellites, orbiting Carbon Observatory 2, I guess they finally got that up. There's the NASA A-Train, Aqua, several different satellites that look at the Earth for a lot of different purposes. It's kind of interesting to me. What you see here is some of them are looking down, and some of them are looking off at an angle. The ones that are looking off at an angle are doing what's called limb sounding. They look, as the Earth is like this, they'll look tangentially at the atmosphere with a bunch of slits and move it up and down. And then from the geometry, you get the altitude you're looking at. Of course, you're looking through a curved surface, so you have to correct for the fact that the atmospheric path length is different on the altitude. But they know how to do that. You can get a lot of things like carbon dioxide concentration, ozone, water, and various radicals like OH. That's a product of combustion and chemical reactions. And then some of them are looking down, and that's a really interesting thing called sounding. If you look straight down through the atmosphere, and you look in these microwave frequencies, and you look in very narrow frequency channels, what it does is it picks out either oxygen or water vapor in quantum mechanical states that are associated with the pressure. And of course, pressure is altitude. So you can actually get an idea of the temperature and the concentrations of oxygen and water vapor. And these are the various pressure altitude channels. And you can see there's overlap, so they have to retrieve. It's called retrieving the data. But it's an interesting thing that satellites do. And they're used for virtually everything. Our life depends on satellites nowadays. But there's a problem. Before I say that, crop management, algal blooms, destruction of Hurricane Katrina, the tidal wetlands, watching hurricanes as they move, predicting them. They're constantly recording the temperature and the moisture content, and that gets fed into those weather models every 6 hours as the satellites go over. So this is a way they do more accurate weather predictions also. So they're extremely important to our civilization. There's a lot of space junk. And for instance, there's over 150 derelict upper stages in orbit. They're all blown up there so you can tell what they are. They wouldn't look like this if you were up there. They would be just little dots. But if anything, at 7 kilometers, a little particle can blow a hole in a satellite and just tear it to pieces, and that's $500 million down the drain. So there's a lot of concern. I think in 2014 they had to move the International Space Station 4 times. That's expensive and difficult to do to a slightly different orbit to avoid some space debris coming by. So it does eat into our taxpayer dollars. So I got to do some orbital debris research. This is a satellite I built, rocket engine, fuel tanks, and so forth. And we fired a particle at it. That's me mounting it in a big vacuum chamber at Arnold Air Force Base near Tullahoma, Tennessee. And that's the gun. They throw bags of gunpowder in there, fire the gun into a vacuum chamber that's about a football field long. And I was down in the middle of that. And the chamber's in the other room, that's why you can't see it. And this is what we saw. So you'll see the penetrator coming in here at 7 kilometers a second. It just turns it into plasma, white hot plasma. Now what nobody had seen before were these colors, which are what indicate the chemistry that's going on in there. So that was one of the discoveries that we made in this work. I was going to show you the input. I was going to show you. There it is. So that the penetrator's there, bam. But now you can see the chemistry. This is aluminum hydride coming out here in the blue. So that's something new that we did because it turns out that that gas of aluminum can actually make little flakes like corn flakes. Only they're made out of aluminum. And they have enough power that they're like at orbital velocities, they're like a 50 caliber Browning machine gun sniper round. Imagine shooting that at a satellite. So they're very powerful. And they can't see them from the ground with radar. So it's a big concern right now. So I'm going to do another wipe now into rocket engines. So this is some work that I did at ATK in northern Utah. They're the ones who built the shuttle solid motors. They build a lot of other rocket motors too. I had built this. This is about $500,000 worth of remote sensing equipment. 1 year of junior college. That's as far as he got in the school system. But he got really pumped, and he read this book. And there's another book just as big that you can download for free that tells you how to build a rocket engine, how to design it, the tests you have to do and everything. And he did it, him and his buddy, in his buddy's garage. Richard Ornelas is his name. And I found out about it and I said, hey, and I started giving him money as a contractor so I could take data off of his engine. So this is what it looks like. Oops. So here's my computer model of that engine. You can see the ignition here of the shear layer. And what's going to happen is we're going to chop off. Now there's no LOX. It's a LOX kerosene engine. This is just kerosene burning. And that black stuff is particulate matter 2.5, which is what comes out of diesel trucks when you see them. What it is when you don't have enough oxygen to burn the fuel at those high temperatures starts reacting with itself. This is characteristic of hydrocarbons. So here you see kerosene starting out, and it begins to what they call cyclize and form polycyclic aromatic hydrocarbons, bigger and bigger until they start to go together into sheets, and then they curl up and form particles, and this is soot particles. But it's constantly doing this, so what you wind up with is soot particles coated with polycyclic aromatic hydrocarbons. And they're small enough for you to inhale them. So that's why they outlawed city diesel trucks some years ago, because of the cancer this causes, deep lung cancer. Because you can't get rid of the polycyclic aromatic hydrocarbons. So I guess Trump is taking apart the EPA, which is one of the reasons I had to retire, take an early retirement. But I suspect maybe the next administration will reinstate these things, because this becomes a medical problem, because guess who pays for people with lung cancer? It's us, in our insurance premiums, in our taxes. Okay, now we can start. Okay, here. My apologies on that. So this is pre-launch takeoff. And there you can see the launch deluge water coming on. And the reason they do that is because this flame coming out is so hot it'll melt the launch pad, and that's a big waste of money. So this is a very common thing. This is the launch pad water evaporating, and this is the PM 2.5. The rocket lifts off. But in the lower atmosphere, all the PM 2.5 burns up, so you don't see a soot trail. That's why it's so bright. It's because this is the PM 2.5 burning outside the rocket. That's a big efficiency penalty. And if you look close here, you can see flames flickering around the rocket engines. That's because the gas generator is dumping PM 2.5, but then it gets swept out and ignited by the hot plume. Now it's gone up through the atmosphere, it's starting to turn over. There's less atmosphere around, so the plume is starting to spread out. But what actually happens is, you can see it spread out. Now it's not so bright, and the reason it's not so bright is because afterburning is shut down. There isn't enough air up there to burn up the PM 2.5. There's a little bit of burning going right at the front, but it's just dumping this PM 2.5 into the upper atmosphere. That's got a lot of scientists really concerned about global warming, for instance, because this is in the upper atmosphere. And then there's another group of scientists who are worried about this. You see all this brown stuff? That's the PM 2.5 now in the orbital transfer. That's getting dumped up into the orbits where our billion-dollar weather satellites are. So there's concern about that too. But there's a lot of drama going on in the government right now, so they're kind of ignoring this. And the Air Force, where I worked, who's in charge of this, the commander-in-chief is the ultimate boss. And if he says, ignore that, guess what they're going to do? Even though it's a problem. That was another reason I retired. So here's the last of this series. This is a static firing. We have the white steam from the water, and then the black PM 2.5. This is going on every week in McGregor, Texas. And that's a huge amount of kerosene they're just burning up there. They don't believe they believe in burning it and making tests. And, oh, that didn't work, let's try something else, they'll burn another one. Well, that worked a little bit, let's try something else, they'll burn another one. So that's why they're doing so much. But see all this? I mean, it's 4 miles from McGregor High School. You can even go on Google Earth and look at this place, and you can see a black patch on the ground pointing towards McGregor High School. Again, the government says, well, actually SpaceX is lying to the EPA about this. They told them this doesn't exist. So, what do you do? I don't know what you do. Okay, now a cut to the Holocene. This is the core of the talk. So, Holocene. Does everyone here know what the Holocene is? No. Okay. Well, here's some points to remember. CO2 is the single largest waste product produced by the human race. Transportation is a big cause of it, but also concrete manufacture. You never hear anyone say that. But when you make cement, you have to bake the lime. What you get is 1 molecule of cement and 1 molecule of CO2. So every time you see cement, say a 50-pound bag, you know 50 pounds of CO2 went into the air to make that 50-pound bag. And that's not counting the heat, you know, the electricity or whatever they use to roast the lime. Also, of course, power plants. But yeah, concrete is the second most used material by the human race after water. How do you like that? So concrete is a big deal that nobody talks about. Okay, what is the Holocene? Okay, these are 2 different ice core datas of global temperature going back 450,000 years. It was really turbulent, in and out of hothouse Earth there and ice age Earth here. And our species, okay, humans have been around for a couple million years, very Neanderthals and some other species, but our species, sapiens, appeared about here about 200,000 years ago. So we lived through the Eemian and through all these ice ages. And what's interesting is we didn't do anything. Until about 80,000 years ago, this cognitive revolution. All of a sudden what they see in the archaeological digs is we're starting to carve things that didn't exist, like half lion, half human. That kind of thing. It's like, wow, what happened? No human had ever done that. All of a sudden, this species is doing it, our species. And then shortly after that, we left Africa, colonized the first large animal to colonize Australia, first large animal to cross the Americas from Asia into the Americas, because there was in an ice age, the sea level goes down, so there was a land bridge. So we learned how to live in the Arctic, basically. We invented the needle and could make clothing that would keep us warm. So, I mean, all these things happened here, but it was still in and out of ice ages. So not much beyond colonizing happened. And then something miraculous, I mean, I don't know what else to call it. Right here, the Holocene began. The Holocene is this 10,000 year period, as Hariaksha kindly mentioned in the introduction, when the climate suddenly stabilized. And it's been stable for 10,000 years. That's when we started agriculture, we started towns, we started cities and civilizations. Everything around you is because of the Holocene. If that hadn't shown up, we'd still be hunter and gatherers, and I wouldn't be telling you about facts versus opinions. So anyway, I tried to put references for everything down at the bottom of the slide. So if you want to look it up, just grab your smartphone and take, or I can send you the references or whatever. Hariaksha, I think, had a sign-up sheet, so you can just shoot me an email and I'll give you that. And I'm also going to put this online. That's why I'm recording it there. So we depend on the Holocene. It's that simple. So we really don't care about previous ice ages. If you're talking to somebody that said, oh, the Earth always did that, no. 10,000 years ago it stopped doing it, and that's why we have our civilization. So we kind of like to keep the Holocene. I mean, I like antibiotics. I have an artificial hip because of antibiotics. So, except this thing now is happening, and we know from the modeling and the chemistry, the facts I showed you, that it's because of the carbon dioxide in the atmosphere. We've known it for 200 years. These are all the thermometer readings in the northern hemisphere, just put together on the graph. The most frequent readings are at the hump, wherever it happens to be, and these are much less frequent out in the tails of the hump. And so 51, then the 80s and 90s, 94 through 04, 05 through 15. So you can see it's getting hotter. But what really matters is here. The number of extremely hot days has been going up. And if one of those extremely hot days happen 3 weeks before your crop is coming in, then you're going to have a crop failure. Not to mention things like changing rainfall patterns and so forth. So this is what really matters. But it's hard to talk about this stuff because it's complex. As you can see, I've been flapping my gums for over half an hour. So this sort of encapsulates the problem. This is going back 700,000 years. So humans appeared about here. We were hunter and gatherers all this time until that little blip there of 10,000 years, which is the Holocene.
Okay.
Yeah.
Question. Did we cause the Holocene, or what caused it?
Yeah, scientists don't know for sure. The Earth system, in fact, what they're doing right now is working harder and harder at applying those Navier-Stokes equations and the chemistry equations, but also geology equations, because over geologic time, as water washes down a hill, it carries minerals with it. So there's a cycle there. There's a nitrogen cycle, and they have to try and capture all this. Why did this happen? Now, my opinion is, now this is just an opinion, there are some scientists who think what happened is it's like a pendulum that winds down and gets steady and then stops. And so it's jumping around trying to find something. And when ice ages come, then trees die, and then volcanoes happen that cause it to warm up again because they spit out a lot of CO2 and sulfur dioxide. But everything kind of got in sync, and it took millions of years to do that. So, but the problem is here, we're kicking it out of sync. About 10 times faster than the end Permian mass extinction, which was caused by the, has anyone ever heard of the Siberian traps? Okay, there's this formation in Siberia, traps means steps. It's a volcanic, like you've seen sometimes the volcanic layers on the hills here. This one's like a mile thick and goes for not a mile, half a mile. It's huge. So there was many thousands of years of gigantic eruptions, and that spewed enough carbon dioxide into the air to warm up the atmosphere enough so the cold emitted, and then methane comes out of the permafrost and all that. So it became a runaway. In fact, now basically all the mass extinctions, they're calling them thermal, except for the meteor one that killed the dinosaurs. They call them greenhouse mass extinctions now. They now understand. They didn't know that 20 years ago. But so we're kicking off another greenhouse mass extinction. This particular set of data is based on the observations. So this isn't the Navier-Stokes equations being solved in a global climate model. This is geologists who have studied the past, predicting what the future will be based on what the past was, or measurements of the past. The problem is, it's heading for much hotter than whenever humans were around. And now that's bad for civilization, because civilization depends on the Holocene. So now they're beginning to look at how do we keep the Holocene stable. There's this Rockstrom where's Johann Rockstrom? The Potsdam Institute has come up with this way of looking at it called planetary boundaries theory, where they say we can't push the planet beyond certain boundaries in several regions, like the water cycle, the nitrogen cycle, climate change, biodiversity, things like that. Because believe it or not, the bacteria in the ocean affect the carbon dioxide cycle. You know, it seems bizarre. You think only volcanoes could do that. No, life affects these things. And it's very, very complicated, but we do know, you can see dates here. So right about here is where we are now. So we know this is heading up, and they project based on knowledge of how the physics of the planet has worked. So it's a concern. And the IPCC back in 2014 said we need to stay below 2 degrees C. Reasons: the 2003 European heat wave had a huge death toll. The Russian heat wave killed tens of thousands. That was from the Center of Research on the Epidemiology of Disasters. The 2010 Russian wildfires, drought and crop failures. 2012, the U.S., I was listening to a talk by Lester Brown, the U.S. lost 30 or 40% of its wheat crop due to a heat wave that just sat over the Midwest. So there's a big concern that we won't be able to keep civilization going under these kinds of conditions. This was 2016, the last time, the best information I had, the last time that I gave one of these talks. So Canada had the Fort McMurray fire, just erased a town 2 or 3 times the size of Prescott. The Crown Fire. I talked to some, you know, on that Earth Day thing out there, they bring the fire trucks out. I was talking to the firefighters, and a couple of them went there to help from Prescott. Wow. And she said, yeah, it was just a big Crown Fire. There's nothing to do except get out of the way. Asphalt melting under extreme temperatures, Vietnam and India. We know sometimes you can't take off planes from Phoenix. It's so hot now they can't take off. They just weren't designed to. Rail lines buckling, that's expensive. And you can't move food or people with buckled rail lines. Great Britain and Australia. This information I just got, Stuart Scott attends all the COPs, which is the Paris Agreement that they had a while back. It's conference of parties. This one was in Poland, and he collected some information. California's 2 wildfires that were just out of control. Canada had another wildfire just a couple of years after the, and that's pretty far north in my way of thinking. They must be getting awfully dry. Greece, not known for wildfires. Siberia, remember snow? I mean, I thought they sent you to Siberia to get rid of you. Wildfires. Denmark, not known for wildfires. Sweden, not known for wildfires. So this is what happens to forests as they dry out, as the land gets warmer. As the air temperature increases, more moisture goes up into the air and leaves the trees dry. Another thing he pointed out was the second warning to humanity. 15,000, close to 20,000 scientists now from 164 or more countries have signed this. And what they're saying is a great change in our stewardship of the earth and the life on it is required if vast human misery is to be avoided. Basically what they're saying, if civilization is going to fall apart. I should have handed out Prozac, I'm sorry. So here's a real sensational out of Bloomberg. How to adapt to the end of the world. You know, these things are always doing these sensational titles. Okay, yeah, that's sensational. It's not that. Here's what they're talking about. Social collapse. That's one to ponder on. What does that mean? Maybe the police won't be around, or maybe like Katrina, you'll wait days after a disaster before FEMA makes a feeble presence, or something like that. And that, you're beginning to see civilizations unwind. So there's concern about this and talk at very high international levels. How do we deal with this? In fact, many nations are building walls to keep out climate refugees, because it can result in adjacent nations collapsing. I don't think that's true for us, but if you're a small nation and you get flooded by refugees, that can just tear things apart. I'm trying to remember a collapse, and I can't remember it. It was after World War II in the Ukraine. I can't remember. Maybe it'll come to me later. So another reason. At 4 degrees C, they want to stay below 2 degrees C, but if we let things run away at 4 degrees C, in North America, we're looking at 20 degrees increase. So imagine every summer in Prescott, 110. Average, and then heat waves on top of that. Half the food crops. You can't rely on food anymore. That's what the Holocene meant, as Gregor Nauer correctly pointed out. Stable. Every summer, you know there's going to be a growing season. You can make a farmer's almanac. You know when to plant. You know how much your land's going to produce about. That's what civilization needs. Continual food supply. So if we start having crop failures, it becomes very difficult to maintain a civilization. Fatih Bartol, the IEA chief economist, says 6 degrees and it's all over. The World Bank and the IMF says 4 degrees C would probably collapse at least parts of civilization. And there's an equity thing. It turns out it's the top 10% of the world's wealthiest who are doing this. So I'm going to say more about that in a minute, but there's going to be more talk about this in the coming couple of weeks when the Northern Arizona Climate Change Alliance makes a presentation. But these are the two that were released, and this is one of the reasons I think there's some interest nowadays. The IPCC and the US are both saying 2 degrees C is too much. We need 1.5 degrees C if we want to be sure and hand a future to our children. So this is the primary piece of information out of those, is this figure. And you can download the executive summary, scan through this figure, and then start reading some of the words about it. It's pretty interesting. There's 4 scenarios for 1.5 degrees C. But what's really interesting is that these 3 are garbage. They're based on absolute scientific fantasy, not the facts that I'm here talking about. Because they were created by economists in the working group 3 of the IPCC, not by the physicists who know facts of all things. But policymakers love these, because here you can push out any serious action to 2050, whereas this is saying we got to do something in 5 years. So if you take away this geoengineering, it's called BECCS, by the way. Has anybody heard of BECCS? Yeah, so it stands for Biomass, Energy, Carbon Capture, and Storage. This is this plan they've come up with. The economists, we all know economists know everything. They're just the ones who crashed the economy in '08. So here's the 4 scenarios. We're on this one, which is the worst one. It's setting us for about 8 degrees F. And they're saying we've got to go on this one, which is that right there. It's turning over. And this is gigatons of carbon dioxide released per year. So a gallon of gasoline releases about 20 pounds of carbon dioxide. So if you have a 20-gallon gas tank, 20, that's 200, 400 pounds of carbon dioxide, for instance. And a little further along, I'll mention some more information about that. So we're only going to concentrate on this. But what they did that was really right, they haven't done in a while, is they said this. This scenario here, a downsized energy system, enables rapid decarbonization of the energy supply. Downsized energy system. What does that mean? It means we're going to stop using energy. That's the only way we can turn this thing over. To me, that's like, oh boy, I better get some solar panels in so I'll have electricity when the grid goes down. But it means a lot of different things to different people. Now, a lot of people will say, well, we're going to use this or that technical fix. You know, like we'll build carbon capture, carbon drawdown. And I see some shaking heads back there. I'm going to talk about that. Only 20% of our current energy use is in the form of electricity. And things like air travel can't be electrified. There's actually a reason for that. If this were a lithium-ion battery, it's not. It's NiCad. But if it's a lithium-ion battery, that's about what you need to replace a tablespoon of jet fuel. So there's a factor of 20 there. So imagine a jet airliner with 20 times bigger gas tanks. I mean, you'd only have room to carry 5 passengers on a 747. Never mind the fact that their jet engines only run on jet fuel. So you'd have to switch back to propeller planes. So you can kind of see where this is going. Commercial air travel is a big problem when it comes to climate change. Another thing, to have all of our energy, since electricity is only 20% of our current energy, we'd have to have a grid 3, 4, 5 times bigger to power everything. So that's a big thing. Imagine installing all those new wires. You know those big things they have? They're like steel cages that have the super high voltages on them that you see marching across the landscape out here. I forget what they call those. Transmission towers. Imagine everywhere where you see a transmission tower, there were 4 more. So there's 5 of them marching across. That's the scale of effort we're talking about to switch to 100% electricity. If we try and use as much energy as we are now, if we do what that IPCC report said, decrease our energy use, then we have a chance of using our existing structure. But it all depends on us changing our habits. I got one for you. It just popped into my mind. So this is a demonstration about habits. I want to do this at the beginning. Okay, so everybody, fold your arms. Okay, so look down and see what hand's on top. And then let them down. Then fold them again. And so for me, the same hand was on top. How many people had the same hand on top? So most people. So that's not it doesn't make any difference, but it's a habit you get into because you shouldn't care about it. I mean, you just want to fold your arms and get on with the day. You don't want to stop and think, well, what's the optimal way to fold my arms? Okay, now something. Fold it with the other one on top. And it works. But you had to think about it.
It feels awkward.
And it feels awkward. So that's the thing about changing habits, like decreasing our energy. It's going to feel awkward, and we're going to have to think about it. And a lot of us are like super busy, and we don't want to think about stuff. But that's what we have to do. That was just a little thing on habits. And we have to change our habits because we don't have big enough transmission lines. That's at least one of the reasons. And we're going to have to stop flying, basically. And where would we get the electricity anyway to have a 5 times bigger grid? Well, we would need 4,000 nuclear reactors, which would take hundreds of years to build. But we have 5 to 10 to stop global warming at 1.5 degrees C. So we don't have time to build anything to do that. That's why we have to change our habits. And also uranium is a non-renewable resource. Once it's gone, it's gone. The nice thing about solar, wind, and tidal power schemes is they're renewable, which is nice. But you have to build huge numbers of these things, and that takes time. And the other thing is, anything you build is going to be made out of concrete. And remember, concrete is very high carbon. 1 pound of cement equals 1 pound of CO2. And these are things people don't talk about, but we have to start talking about them and be aware of them. I don't know if we'll be able to, tell you the truth, but it's what we should do. So here's the carbon drawdown crowd. They've actually built some units. Sure, this is simple stuff. They've known how to take carbon dioxide out of air for hundreds of years. And each one of those has a big electric motor and a fan, so you can imagine it's an energy hog is what it is. But now, I did a calculation once where if you build one of these that's a mile long and a mile high, there's 4 quadrillion tons of atmosphere you have to pump through that. That would take like 500 years if you got it going 60 miles an hour through those fans, which it doesn't do. So even if you had a magical thing, it would take too long. And then how much energy is that going to gobble? Well, it turns out, there's this heating, air conditioning, and ventilation, rules of thumb, how much it costs to pump air in terms of electricity. If you calculate that, it uses as much electricity as the whole human race. So it's going to be at least extraordinarily difficult, and there's no value in CO2.
And if they pull the carbon out of the air, then what do you do with it as a waste product?
Yeah, it's just a waste product. It's not like gold. That's what I was going to talk about here. Like she did, just speak out. I was in the middle of talking when she raised her hand, and it's really hard for me to interrupt an idea because I'll forget. So if you just speak out like her, wait till I pause and then just speak out. That's how it happens. I'm sorry, I don't know a good way to say that to people. I talk too much, interrupt me. How's that for honesty? So the way I frame it is mining a highly dilute resource. In this case, gold and seawater. The price of a gram of gold is about $40. And the cost to run electric pumps, that's very well known. Pumps are used everywhere now. The cost to run 100 million tons of seawater through some magic machine that recovers gold, just the electricity cost is $15.6 million. For $40, this is why nobody mines gold in the ocean. Well, we're trying to mine carbon dioxide out of the air. Now, it's 1 million times more concentrated in the atmosphere, but you still have that problem of pumping it. So you could get maybe a 50% profit if CO2 were as valuable as gold, and if we had a magical apparatus, but it isn't valuable. So what they do to answer her question is, so there's this thing in thermodynamics called a triple point. There's a temperature above which carbon dioxide can be a liquid only under pressure. So they have to pressurize the carbon dioxide until it becomes something like a liquid, but then you have to keep it under pressure, so they're going to pump it. The concept is to pump it underground in mines. That's a gamble. And it's all being done because we don't want to change our habits of how much energy we use. And yet that one chart showing that we have to stop using energy should be burned into everybody's mind. Because there's no way around the facts any more than I can stop the magnetic field from making that lamp light up or stop gravity from pulling this down. Just a fact. It's an inconvenient fact, and of course politicians may not get elected if they mention the facts. Here's Bex, and here's what Debbie was talking about. They want to pump the carbon dioxide underground. But the problem with this is when they talk about this on the news or something, they say, oh, we're going to use Bex. And what that does is that make you think you can get away without decreasing energy. So it actually takes away from the solution to even be talking about this stuff. And the international scientific community now is screaming to get the IPCC Working Group 3 economists off the table. They shouldn't even be in there because they're not scientists. So we don't know how that's going to pan out, but things have been getting better. For instance, these two special reports now are calling for 1.5 degrees C, whereas in COP21, the Paris Agreement, 1.5 degrees C was just a maybe. We were heading for 2 degrees C. Well, now they've realized, no, we got to go to 1.5 degrees C. So the knowledge is continually chasing. The other thing is they want to use a land area 1 to 3 times the size of India to do this. What are you going to do with all the people who live there? I mean, there isn't a place to do this. So it's just one of those bizarre ideas that policymakers like. And see, I had that problem too. I had to get funding. And if the government doesn't want me doing research into SpaceX, I'm not going to get the funding. And I was lucky enough to have an early retirement I could take. And if you're a kid out of school with a $100,000 debt, you're going to take any job that comes along. And so that's kind of the problem we're having here. So this curve is the gentlest slope we can decrease our carbon dioxide generation and avoid 1.5 degrees C. This area is the actual carbon tonnage, 700 gigatons, and it has to stay the same. The problem is, if we release more carbon now, our kids have to release less, if that's even possible. And then what happens is, the area under this curve has to stay the same. So the longer we wait to start it turning over, the steeper it gets, until we hit a brick wall, and we're forced to exceed 1.5 degrees C. And this is an animation. This is actually the data. If we keep emitting, here's the brick wall. And at that point, it's guaranteed we're going to go over 1.5 degrees C. We may exceed it already as of 2016. And it's 2035. I don't know whether I'm going to make it to 2035. I'll be really old when I get to 2035. But it'll be 50% hotter than 2016 or now. And you can see wildfires everywhere. And it's going to be a serious problem. And it'll continue getting hotter for the rest of the century, decade by decade. So if we had started in 2010, it'd be a gentler slope. If we had started in 2000, an even gentler slope. So it just gets more and more difficult. So who's doing this? I should go through these slides rather quickly, sorry. But this is the top 10% of the human race. 700 million people are responsible for basically half of all the carbon dioxide emissions. That's 10% of the human race. There's 3 billion people who are responsible for about 40% of the carbon dioxide emissions, and 3.5 billion people who are responsible for only 13%. So when someone tells you it's a population problem, that's not really right, because you can get rid of 3.5 billion people. Just send them somewhere else, to Mars, whatever, and it won't change anything. These are the only people who have the ability to stop climate change. These people can't. And I'll show you what that means. So you can just ignore those folks. So what does it look like? Well, in a more observable form. Another thing you'll notice. So here's China. U.S., by far the biggest. European Union follows it by a little bit. China's way down here. Now China's big here. They have a lot more people who are living on $1 a day or something. So they're big in this area. So this is what it looks like. These are income deciles, 10% increments of income from 0 up to the highest category. So this is the top 10%. These two together make the top 20%. These three together make the top 30%. So it looks like this. These people down here live on $1,000 to $10,000 per year. They have no carbon footprint. If they stopped completely emitting carbon, it wouldn't do anything. These are the people with a high carbon footprint. Anybody making over $20,000 a year. But there are lots of people in the U.S. making $200,000 a year, or even $2 million. I guess DiCaprio's averaging about $20 million a year now. So these are the people with the very high carbon footprints. They're the only ones. And what that says to me is this. These billions of people can't stop it. These are the only people who have the option of saving civilization. And that's us. So this is those people living on $1,000 to $10,000 a day. This may be what the future of civilization, if we can maintain it, is going to look like. He's got a family, kids. He's trying to get a job tearing apart ships in India. Now look at his teeth when he talks. He's what's called a cutter. There's the ships. They do the. So this is the middle class there. $5 for a day's work. He's ecstatic. So he's got no carbon footprint to speak of. He can't. They don't have the option. Now here's an American sort of modest vacation. One of my friends our acquaintance drove a motorhome dragging a small car, 1,500 miles or so. Never do algebra in public. I was told that. So I did it beforehand. 20 pounds of CO2 per gallon, about 7 miles to the gallon. So he came up with 6 tons of CO2 into the atmosphere for that vacation. This is just a modest vacation. And then if 10% of America takes vacations on that order, that modesty, then that releases about 4 gigatons of CO2 per year. And that's not a big deal. It doesn't seem like, but in the grand scheme of things, that's about 10% of what the world releases. So these are just scaling things. These are not meant to be super accurate. These are just telling you order of magnitude effects. But what's true is cars and trains and ships maybe can be electrified potentially using renewables and producing no CO2. But air travel cannot be electrified. Jet fuel equals a lithium battery times 30. So air travel's a big problem. So, and also remember capitalism. That's what we're talking about. Why do airliners fly? Because we buy tickets. If we didn't buy tickets, they wouldn't fly. So you can't really blame the airline industry.
Isn't there a company that's starting up out of the Prescott Airport area? It's an Israeli company. It's electrifying airplanes.
I'm not saying you can't fly. Remember there was a person who flew under pedal power. A bicyclist flew across the European Canal. I mean, you can do things like that. What I'm talking about is commercial air travel as we know it today. So you can build an electric airplane, but it's not going to take you to Europe. Unless it's something like the Gossamer Condor or something like that.
Or unless
Like
they
60
change.
miles or something like that.
Or smaller airplanes.
Yeah, but it's not the commercial air travel. You know, there's 100,000 air flights a day. At any one time, there's 10,000 in the air.
Aren't there some new battery chemistries on the horizon?
There's a couple of chemistries that they haven't figured out how to really work with yet in the lithium ion. They're expecting about a 20 to 50% increase in energy density, but they need 20. And then if you even got that, Well, you have to go back to propeller planes because it's an electric motor you're powering, not a turbojet. And propeller planes can't get up at high altitude where the smooth is. They don't fly that fast. So any way we look at it, it's going to change. So the question is, how much of the world's resources do we want to dump into air travel? Because what this really is ultimately is that we're at the wall of available resources. And you know how they get lithium now, right? There's these giant salt pans around the world, like Death Valley, they're in Africa, they're all over the place. And what they do is they just drill a hole and pump hot water down there and dissolve the salt, bring it to the surface, let it evaporate. There's no mining involved. They're basically just picking up the lithium off the ground. That's like totally cheap. If they have to go to where they're doing deep hard rock mining to get lithium, that's going to make lithium 10 times more expensive. So it's not clear that even lithium ion is going to be something we can sustain. You've heard of sustainability and resilience. They're two different things, but they're related to each other. Sustainability is like you don't harvest the trees faster than they can regrow. So that's a sustainable way to harvest trees. Same with fish. You don't empty the ocean, you let them reproduce and you harvest at the same rate they're reproducing. That's sustainability. Resilience is the ability to absorb shocks, like Hurricane Katrina, like Sandy. You know, those cost our economy huge amounts. And if a big enough disaster happens, like if the Yellowstone supervolcano blows, that would like end America. You know, we just wouldn't be able to respond to that, and that's too big a shock. So now they're talking about preparing for these climate problems by making your community resilient. You want to have a food supply that's guaranteed, a water supply that's guaranteed. Water? Prescott. Oh. So resilience and sustainability are related. Why are oil and gas extracted? Why is food turned into gasoline, corn ethanol? Because we drive trucks and SUVs. If we didn't do that, they wouldn't do that. I mean, this is capitalism, going back to that. Why are carbon-intensive goods manufactured, like cars? Because we buy them, not because they're in the business of making them. So, I mean, it's, you know, our choices and our comfort level that's driving all of this. But the problem is, how do you get this message out to 300 million people in America, or 7 billion around the world? So here's an egregious example. I'll try and wind up soon. This dude, DiCaprio, makes about 20 million, and if you apply the methods that I showed those other charts about the wealth, the relation between wealth and carbon footprint, he makes about 20 million a year. So that he has a carbon footprint of about 900 Americans. Private jet, private yacht, look at that thing. Private helicopter, private island. So that's a huge carbon footprint. So about the carbon footprint of 1,500 Europeans, 9,000 Africans, or 25,000 Zimbabweans. This is from Kevin Anderson's calculations. So this is how wealth plays into this.
Just an FYI, we will be closing in 10 minutes.
I better thank you very much. So there was a cute things to say this. Nonetheless, what we do to limit global warming right now matters a lot. Because anything we do now will make our children's lives better. It can make the difference between a world our children will want to inhabit, one which is very difficult, or one which is virtually uninhabitable. A fundamental response is for the community members to decide what is important in their community. What do you think Prescott is? Because you, us, we're the ones who are important here, not the buildings, not the roads. It's what we think Prescott is. Okay, this is well understood now. So I'll just throw this in. The Anasazi drought was here. This is where we are now. This is 2020. So we're about at the level where the Anasazi drought. Now, we can pump water out of the ground, but remember, that's finite. We have to pump it out sustainably. But it's going to get worse in the future. So these are things we have to think about and talk about, and not pretend they're not happening. Like, pretend that if I let go of the coin, it's not going to fall, or it'll go up, or turn into an elephant. You know, we know what it's going to do. So when I'm retired, I got my carbon footprint down to here. That's not enough. It needs to be here. Here's an average American. If you ever see anything about offsetting, that's been discredited. Just ignore that. They keep it up in U.S. websites because of our commander-in-chief. So here's something I did. I painted my roof white. Okay, here was my attic temperature in the summer, those horrible summers we had last year, 150 up there. And then heat comes down, and you want to go to bed, but you can't, because it's like 90 in your bedroom. So you got to do something. But then I painted the roof right, and here's my attic temperature now. It's below 100. It's basically at the outside air temperature. So when I go to bed, it's almost perfect. I can crack the window for 10 minutes, and it's comfortable. So that's a big difference in that electricity bill. And I'll mention the electricity bill, maybe I should wind up with that. So here's 1,000 kilowatts. Depends on your lifestyle. If you have a big house that you air condition heat, that's probably really low. If you have a small place, this is pretty high. But you can go on to EPA.gov, and that turns out to be about 1 month is 1,700 miles in a car. That's the amount of CO2 you're releasing. I thought this was good. 30 cylinders of propane. So if you really like to barbecue like every night, that's equivalent to 1 month of electricity. This is misleading. They say here tree seedlings grown for 10 years, but I'm making that carbon dioxide in 1 month. So I actually have to have 1440 tree seedlings running every month to suck out the carbon dioxide I made that. That means all of us have to have that. And now you're talking more than there are trees around. But you can just go on the EPA and you can see 30 bags of trash that you recycle. I don't even make 30 bags of trash in a month. So you can't do this and offset that. This has to get smaller, and that's what we're talking about with that carbon curve going down. People have to stop using energy. Luckily, a lot of people have realized this. There's this transition town movement happening all over the world. Hopkins Center for Livable Future has published a report on their food system. They're looking at how do we deal with these problems for our kids so that we're sure they're going to have a sustainable food supply. Other major publishers and so forth. This is a really good book. There's a copy right there. Energy and Authoritarianism. We probably don't want the feds doing this, but Arizona State University has a community resilience master's degree they offer. So we do have resources. Prescott Online College. What we do to limit global warming right now matters a great deal. A fundamental response is for community members to decide what is important in their community and to take early action to prevent that. So that's what we're doing here. Thank you for your attention and time.